So P of t is 1,000 times 1.04 to the t. We want to find P of 10. Okay. Bad look at zero there. Okay. P of 10 is 1,000 times 1.04 to the 10th. And we just plug that into the calculator, right? And I think everybody, got that. So that's approximately equal to, was it 1440? Yeah, something like that. I'm gonna say approximately equal to 1400, but you've got 1440.84, something like that. So people pretty much got that, right? Everybody good with that? That's what it was asking. That's how you solve it. Okay. What are you going to solve? You've got to remember what we did last week. So if you don't remember, if it didn't jog your memory to see this, well, it should. I'll show you. Okay. So P of t equals 2,000 means one thousand times 1.04 to the t equals 2,000. Now your variable's in the exponent of one of the terms. So what's that tell you? Tells you you're going to have to convert this equation to exponential, right? To logarithmic form. Okay. And that's easy to do, but you can't do it yet. And we did several examples, so you might want to review them if you don't see it. But yeah, we just got to have, I mean, our rule is b to the a equals c is equivalent to log base b of c equals a. Okay, just inverse function property. So we got to understand the inverse function property. Of course, for homework, you solved a number of exponential equations. Okay, now we're trying to apply them and understand this terminology so we can understand how to apply these things. Okay, so I think we have all this here. Okay, so this isn't in this form, but it is going to be a b to the a equals something. You got to see b to the a equals what? Here's your b to the a. Here's this. You want to get this. So you got to divide both sides by 500 and by 1,000 to get this, right? So we divide both sides by 1,000. We get 1.04 to the t equals 2. We solve that. T is the log base 1.04 of 2, which equals log of 2 over the log of 1.04. And that's the step I want to see. Okay. I don't want you to just shortcut it on your calculator, mainly because when you get on the test, you're not going to have a calculator that allows you to do a log base. You got to know that it's log of this over log of this. In any case, now that should come out something around 18, maybe 17. Okay, so punch that in for me and verify that, or prove that I don't know what I'm talking about and let me correct it. Okay, so again, P of t is 1,000 times 1.04 to the t. Incidentally, this is what you would get with a 4% interest rate compounded continuously if you invest $1,000. Okay. So t is in years. P of 10 is how much money you'd have after 10 years. have about $400 more. And there's a question whether inflation beats that or not, but we should have $400 more, right? And usually the interest rates go up when inflation goes up. So usually an investment will keep even with or beat inflation, but you can't count on it. Sometimes it works to your advantage, sometimes it doesn't. And leave it to you to understand enough economics to figure out what to do when. I'm not the one to tell you. Okay. So we evaluate P of 10, that's very simple. Get to 1400. P of T equals 2000, that's an equation. Okay, you can't do much with P of T equals 2000 unless you know the formula for P of T. Unless you know the formula, then you write the formula instead of your P of T. So P of T equals 2000 becomes 1000 times 1.04 to the T equals 2000. That's just a simple exponential equation. But of course, you have to have this form or this form to convert it. Your variables in the numerator, in the exponent, okay? So it's the first form, exponential form, but we don't have b to the a equals c. We have something times b to the a equals c. We've got to divide both sides by that something. So we divide both sides by 1000. Now we've got b to the a equals c. And we can write log base b of c equals a, which comes out t equals log base 1.04 of 2. Just straightforward translation. And that is log 2 over log of 1.04, and that's approximately 18. I think people got 17.63. Okay. Now, what's this tell you? Well, 2000 is twice as big as 1000, right? Among other things, that's how we got the 2 here. Okay. And what's happened to your money? If you start with 1000, you get 2000, it's doubled, right? Okay. So it doubles in about 18 years. Okay. And that works no matter when you start. There's an equation we could solve for that. Hopefully we'll be able to do that, but that's what we get. Okay, well. Graph in an appropriate box. Y equals 2 to the x. Looks like this, where this is 2. I'd like to do the vertical dotted line, x equals 2. X equals -2. Okay. Well, now I'm going to relabel this graph in a different color. Because the graph I want to get is the graph of y equals 1000 times 1.04 to the t. Okay. Now when t equals 0, what's this equal to? It's equal to 1000. 1.04 to 0, 0. So if t is 0, this is 1000. So my relabeling if first of all y equals 1 would be here. Y equals 2 is here. Right. And I see from that that I didn't draw a very good explanation. Okay. Now, I want to do a graph of P versus T. Y equals 1 line becomes the P equals 1,000 line. Because when T equals 0, we got to have 1,000. So this point has to be 0, 1,000. Now in white, I don't want to clutter up my graph too much, but this would be the 0.01. Unfortunate, we didn't draw a very good exponential curve there. So I'm going to try to do just a quick repair on that. Okay, that took less than a minute, came out better than I expected. Okay, this is a better exponential, and I've used the x equals 1 line and the x equals -1 line here and the subdivisions here. Just the usual algorithm for constructing the exponential. And of course, I got a line down here and a line down here that I haven't drawn. But we're really interested in this part of the line anyway. Okay. So between here and here, the value doubles, doesn't it? I mean, I've gone from on the y equals 2 to the x, I'm going from y equals 1 to y equals 2 here. And then here I go from y equals 2 to y equals 4. So your toolkit exponential function doubles every time you move over 1 unit. Okay. Now, where is y equals to p equals 2,000? Where's the line for p equals 2,000? It's this line, isn't it? Okay, if this is 1,000, this is 2,000. So here's p equals 2,000 line. So on my blue scale, what should be the value of t here? T equals what? Okay, people have a little trouble wrapping their heads around the idea well enough to answer, but I point out that what do we do here? We found when P of t is 2,000, didn't we? We solved this equation, found that P of t is 2,000 when t is 18. Okay? That means P is 2,000 on this line. P equals 18 here. Okay? What do we got here? What's t equal here? Got 2 digits. Can you show me with 2? Well, let's just talk about it. Okay, so again, yeah. T is 18 here. What's t here? Well, t is 0 here. This line is as far to the right of 0 as this line is to the right of this one. So if you think a little bit about it, you got to conclude that t equals 36 here, assuming you know that 2 times 18 is 36. Okay? And hopefully you know that. Makes it hard to think about things you can't do the basic arithmetic. And of course, t is 0 here because that's the y-axis, or in this case, the p-axis, right? Okay. So let's say you invest $1,000 because in 25 years, well, I didn't phrase that very well. You invested $1,000 so that someday you would have $3,000. Okay, when's that day going to come? Now, you could solve the equation. You solve P of T equals 3,000, just like we solved this one. It's easy to solve. You don't want to forget how to solve it because you're going to have to do that. You're going to have to do it for the homework and for the exam and all that stuff, right? So you don't want to forget how to make these conversions. Now, open math also tells you take the log of both sides. That's another legitimate way to do it. But I'm going to talk about one way here, okay? Just so as not to confuse anybody. Because open math does it both ways. But the other way is totally equivalent to this. Okay, so again, you set P of T equal to 3,000, get your solution, that's easy. But let's say you don't have your calculator handy and you want to get an idea. Well, you just draw yourself a pretty good graph. Okay. Yeah, you can line it up and try to make it fairly accurate. You know by now that you can often do some pretty accurate estimates. If you've been doing everything I asked you to, is comparing your estimates to your solutions and stuff like that. Okay, and I think most of you have been doing that. Okay, so how are you going to use this graph to solve the equation P of T equals 3,000? Like P of 10 was out of 1.04 to the 10th, right? Here's your formula for P. You just put 25 in there and see what you get. Somebody do it because I'm getting anxious to know whether my estimate was worth a darn or not. I think I'm off by more than one, but maybe.
That's for 25, it's 2,665.
How much?
2,665.83.
2,600 and some? Okay. That's no part of their 3,000. You better have that thing checked out. Calculator. Okay. Somebody's got you some bad software there. Okay, so apparently only one person actually did this, and it would be good if everybody did. If you're taking notes and thinking through something else, that's okay too. Okay, so we got 2,600. That's really pretty terrible. All right. Well, that's what my graph told me. Yeah. It's recorded.
It doesn't hit.
Oh. Okay, you wanted to say something. Okay. Says this happens around 29. Okay, well, let's just see. Okay, so apparently I screwed up some. Okay. Well, it's just my graph wasn't that great. All right, and this line's not exactly parallel to this one. So something's a little screwed up. So it's all of my graph, not my brain. Believe me? Okay, so now solve. P of T equals 3,000. Well, it's going to be just like this solution, except when you divide 3,000 by 1,000, you're going to get 3. So you're going to get the log of 2 over the log of 3 over log of 1.04. Written kind of badly, but it's just going to, you just write out the same thing you did here, but understand why you did it and understand we use these conversions between exponential and logarithmic form to solve it. Okay, did you get something? Hang on. Okay, so what do we have before? It doesn't hit 3,000 until year 29. In year 28, it's only about $1.50 short of 3,000. Okay, and it turns out that if you do log 3 over log 1.04, you get something like 28.01 or something like that. Okay, so it's real close to 28 years. All right, now do we understand how to use and solve these equations? And I'm going to give you another situation. Okay, so we got a turkey. Thanks, Amy, a week from today. A week from right now, I'll probably be cooking a turkey, won't I? Okay. Temperature is in Fahrenheit degrees, T is in minutes. If T equals 0, temperature is 160. If T equals 60, the temperature is 120. Fair enough? Okay. So I want to know what my model is. The other thing is, I don't know what my asymptote is. We talked about that last time. You got 2 points on the graph of an exponential, and you don't know what your asymptote is. You're up a creek. Okay, so the asymptote T approaches infinity, time T, temperature approaches 70. That means that the turkey is in a room at 70 degrees. Okay, because you take a turkey out of the oven in a room at 70 degrees, the turkey's going to approach 70 degrees. Yeah, it might be a little off because of evaporation and stuff. There are all kinds of things that really go on with a turkey. So this isn't a perfect model, but it's not a bad model. And if you're running a restaurant, it can give you a timeline of when you ought to slice that turkey and serve it. Okay. All right. So there's an exponential model. Okay. Temperature is A times B to the T plus K. All right. So what equations do you solve? You get that model. Identical to what we did last time with stretching. So if you've reviewed that, you probably have a pretty good idea. But if not, I'm not gonna let you sit there and beat your head against the wall for more than a couple of minutes. Okay. See if you can write down something resembling the equations that you would solve. Hopefully, write down the actual equations. If you want something to kind of grab onto, get your back. Okay. That's graph that might be close to an exponential curve. I didn't construct it carefully, so it's probably not all that accurate. Just to give yourself a picture. Okay. So it's like if T equals 0, you've got the coordinates at this point, and then maybe T equals 60, you got another point, and you got what the temperature approaches, which means you've got the horizontal asymptote. Okay. So when you're applying a problem, when you're trying to apply what we know about exponential logarithmic functions, it's very useful to think in terms of the graph and points on the graph. And also to the form of what the function should be. This is obviously needs a K because A times B to the T is going to approach 0 as T goes to infinity, assuming it's a decreasing exponential, which it clearly is. Okay. Make sense? Okay, so what can you tell me about these equations? What numbers do we put into these equations? Okay, now you sketch a graph. You know that this thing is going to be exponential. You know it's going to be decreasing, and you know a decreasing exponential has a curve that looks something like this. Your curve might not be as wonderful as mine. It might actually be accurate, which would be a whole lot better than mine. Okay, so but you get the idea. And this graph is just a schematic. We're not going to try to make estimates based on this graph. After we get done getting the function, maybe we'll construct a graph. But right now, we're just using a general picture, just something to sketch in the back of an envelope or something, to draw your attention to what you need to know. So we have all this information here. How do we put this information into the picture? Well, T's here, right? Big T's here, little T's here, big T's here. So as little t goes to infinity, that means as we keep going that way, what's going to happen to this curve? It's going to approach this asymptote. Okay. So that this asymptote is a line where big T equals 70. Make sense? Okay. Then we have 2 points here. What coordinates? Why did I put this point on the t-axis? Because we know that big T equals 160 when little t equals 0. We know what happens when little t equals 0, which is that big T equals 160. So I can kind of draw a line here. Big T equals 160 here, and this is the point 0, 160. And what do we know about this point? We know big T. What's this point represent? Represents this information. This information translates to a point on the graph. So translate all the information you can on an applied problem into points in a graph. Or maybe on the lines that might be asymptotes. Okay, so little t equals 60, big T is 120, so we're just okay. Big T equals 120. Little t equals 60. I like labeling horizontal and vertical dotted lines to help. Okay. Very important for what we're doing, to actually do that. And then we know that the coordinates of this point are 60, 120. Okay, well, I can plug 0 and 160. Little t 0, big T is 160 into this equation. If you haven't done it all right, do that. Plug 0 and 160 where they belong in this equation. Just give me a few seconds to do that. Just do it. I'm not even going to look at it. So slop something down and then see if it matches what I tell you. Okay, either everybody's done it or I'll give you a minute to process. Okay, well, we're plugging in 0 for little t and 160 for big T. So the point zero 160 is this equation. Okay. I just replace big T with the value of big T and little t with the value of little t. And none of that goes in for A or K. Those are values of little t and big T. So what I saw when I went around and you know, half the papers I saw had like 160 for big A or 60 for K, you know, something for B. You don't know A or B, okay? But you do know big T and little t for 2 points, which gives you 2 equations that you can solve for 2 unknowns. Okay. Then you have 60, 120. Write down that equation for me. Okay, so I'm going to put in 60 for what? For little t. I'm going to put 120 in for big T. Since I start with big T, we'll do this. That equals A times B to the 60 plus K. Okay, well, if you transform an exponential function using horizontal shifts and vertical stretches, your asymptote stays at 0, doesn't it? Because the asymptote of your toolkit function is 0. Okay, right there. We started with the toolkit function. The asymptote's at the x-axis. It's at y equals 0. Okay, we can't get the asymptote away from y equals 0 by stretching it, because that just stretches everything out. Yeah, the points close to the asymptote move a little further away, but since they get infinitely close, they're still going to get infinitely close, just a little more slowly or a little more quickly, depending. Okay. The only way we're going to get this thing away from the axis is to vertically shift it. And for homework, you had a number of problems. People seem to do fairly well in those problems, where you were to identify the equation of an exponential function. You know that if the asymptote isn't at the x-axis, you're going to have a plus k. You're going to have to add something to this part. So you want to kind of process that and be sure of that. So anyway, what's the value of k? Well, how far do we have to vertically shift something? Because asymptote is 0 to make the asymptote at t equals 70. We have to shift it up 70 units, right? And right there is our vertical shift. So as t goes infinity, time goes infinity, temperature goes to 100 to 70, implies vertical shift of 70. So k equals 70. So I just write the same two equations down, but k is now 70. Okay. Now, how do we solve these equations? Same steps I used last time. So we have these two equations. Well, what's the first thing we want to do? Okay, so really the first thing we want to do is we want to get this into a b to the t equals form instead of an a b to the t plus some number equals form. And we easily do that by subtracting subtract 70 from both sides. So now we have the equations a b to the 0 equals 90 and a b to the 60 equals 50. Okay. Now, this one is particularly convenient because unlike the example we did in class last time, be sure to review that one. Or, look at the examples open math does, that's fine too. What's b to the 0? It's 1, right? Before we had a number like 20 here and 80 here or something like that for the exponents. We didn't have the convenient exponent 0. B to the 0 equals 1, so our first equation just becomes A equals 90. And then we have A B to the 60th equals 50. Well, since A equals 90, we can plug 90 in for A. That gives us 90 B to the 60th equals 50. Well, then B to the 60th is 50 over 90, which is the same as 5/9. And B to the 60th raised to the 1/60th equals 5/9 to the 1/60th. So B equals the 1/60th power of 5/9. Take your calculator and you can calculate that. Now, somebody would do that, it would be great. Otherwise, I'm going to estimate it, and who knows what I'm going to get. Okay, so we get this. I did this in my head. I get about 0.995. Might be 994, 993, 996. And it might be something completely different. Okay. But that's my best 60-second estimate. Okay. Got your calculator in your hands and we can do that. Okay. So big T is A B to the T plus K. That's going to be 90 times 0.995 to the T plus 70. Now you could plug 60 in for T and see how close that gives you to 120. Might not be too far off. It's not going to be all that close even, unless you just don't look. Okay. So now my question is, when does the temperature reach 100? Which is when the turkey's starting to taste kind of cool. We could estimate that just from this hand sketch graph, right? Okay. Just to get an idea. Okay, so using this graph, if 160 is here and 120 is here, 100 is twice as close to 120 as 120 is to 160. So we can sketch a line here and say, okay, just look to this graph. Gee, it looks like it might take another 40 or 50 minutes. Let's say we estimate T equals 100. Not a good estimate from that graph, but let's just pretend that's our estimate. Okay, so we got some idea. That'll take around 100 minutes, a little after 100 degrees. How do we use the function to do this? Minus T, we take to 100. Well, you solve 100 equals 90 times 0.995 to the T plus 70. How do you solve that? Well, I'll move it. Here, I'll just switch the sides so our variables on this side. And we want to get the b to the a equals c form, so we can convert it to logarithmic form. We subtract 70 from both sides. We divide both sides by 90, we get 0.995 to the t equals 1/3. Better write that out just by itself. The t is log based 0.995 of 1/3. Log of 1/3 over the log of 0.995. And equals maybe 100, probably not, because like 0.995 isn't all that accurate. Okay. And you actually want a couple more decimal places, because what's critical here is how far this is from 1. It's 0.005. Is it 0.0053 or 0.0057 or 0.0048? All that rounds off to 0.995, and all that would make a big difference. And you don't necessarily need to understand what I just said, but it's great if you do. Okay. Bottom line is this is how you solve the equation. So we've taken some data on a turkey. And we've created an exponential model. Now for your homework, you're going to have models like radioactive decay, which is a whole lot like the turkey. Radioactivity decreases along an exponential, except it decreases to 0, so you don't have to worry about the stupid asymptote. Okay? So sometimes you're going to have to worry about the asymptote, sometimes you aren't. You'd also talk about putting the turkey in the oven. What would the graph look like if you put the turkey in the oven? Sketch me a graph. Just tell me the shape of the curve, temperature versus time for turkey going into the oven. Doesn't have to be a pretty curve or anything, just have the right basic characteristics. Most people draw a graph looks something like this. That's a pretty good exponential curve. It looks good. Is that going to be a temperature versus time model for a turkey? Is there a limit to how hot the turkey is going to get? Okay. What would that limit be? The problem with this model is if the turkey approaches infinity, leave it in there long enough and generate nuclear fusion. Okay. That's what this model says. So if you drew this, you have a lot of company. But you aren't quite in touch with reality, no offense. Okay, being in touch with reality takes a lot of work to make. Okay, so what do you think the curve looks like? Can you draw another one? Swap one down. Okay, what's going to happen is, first of all, here's your two maps. Temperature of the oven. Now, the curve is not going to do this. It's not going to go up here and then suddenly. Okay, although that's, yeah. Okay, what you got to think of is the further the turkey is from the oven temperature, the faster it's going to heat up. Because, well, temperature difference. Okay, so yeah, that's I guess a little bit of physics intuition I couldn't necessarily expect. But it's gonna do something like this. It's gonna start at, well, let's just say we start at room temperature. I'm gonna do this. Okay. So let's say this is equals 70 to equals 350. Okay. We want to stop this thing when the temperature is about 160. Okay. The time it takes to get from 70 to 360 is our cooking time. And if we understand this curve, we actually have a little more control of how the turkey comes out. Okay. So if you want to be a good professional chef, really be best if you understood exponential functions. Okay. Now there are a lot of other reasons for investments. You know, that's what we started with here, you have some money growth. Okay. And it gets more complicated from there. And you make the most intelligent decisions, you should have some good understanding of exponential functions. Now you should also listen to good advice from a professional because you might screw it up. And if what you do differs significantly from what a professional tells you, then you probably ought to listen to a professional and modify your model until you have a better handle on it. But just to have an intuition about how money grows, okay, can be useful. And also temperatures and bacteria growth. Bacteria growth in the refrigerator. Okay. Refrigerator goes out, temperature starts increasing. How does the bacteria grow? It doesn't grow much at 40 degrees. At 50 degrees, you start getting an exponential increase in the way bacteria reproduce, and that can save you from food poisoning if you have a little sense. Basically, follow the guidelines because they're pretty considered the guidelines. You probably won't get food poisoning if you follow the guidelines, but you want to understand how the guidelines are and what they are. So there are many practical reasons to understand these phenomena. So it's worth the trouble. So good luck on the homework. You've seen all the techniques you need.